This is an introduction to AI-assisted Colab notebooks. So really AI-assisted programming in general. Why am I going over this? I'm going over this because these large language models like ChatGPT, or in general the GPT model, has gotten so good at programming. In fact, in its release, there is a video that describes one of GPT-3, I believe, not even GPT-4, which is what ChatGPT is. So in GPT-3, way back in the day, as soon as they wrote it, they then fed its own code into it, and I believe it was able to optimize some of the efficiency within itself just because of its general programming knowledge. Now, this doesn't mean that these AI models, large language models in particular, are better programmers. They have a lot of redundancy, sloppiness, and they don't really always get quite right the meaning. And we're going to take a look at that as we go through. What are they really good at though? They're really good at syntax and structuring. This makes sense. They're linguistic models. What do I mean by that? They connect pairings of words. So they take these token values and they're connecting pairings, basically predicting just the next one relative to the current one. And they have certain memories, and that is so good for programming. So we're already seeing them replace what was, a really incredible set of skills that you needed to build up for programming. So how can we still make human programmers in the tech industry valuable, or designers who want to get into computational design? We can leverage these skills, but we can drive them. What do I mean by this? I said that they're sloppy coders, and they are sloppy coders. Well, if we're good coders, then we can augment our own skills with them, accelerating our time for production, but use our intelligence and our standards to clean them and ensure their efficiency and ensure that they're doing what we need them to do. So not only are these incredible machines for creativity and productivity acceleration, but if we use them right, they're incredible prostheses for our own set of skills. So we can build our own skills. It's not to replace our own set of skills. So the idea here even of cognitive offloading, in which these AIs allow us to kind of turn off portions of our brain, that's both exciting and horrifying, and rightfully so. Why is that both exciting and horrifying? Well, it means that we don't have to maybe try as hard. That's maybe a good thing. Why is that horrifying? Well, because as we try less hard, we maybe forget how to do it in the first place. We maybe lose the ability to do it entirely, and maybe lose even the reference to what that was. Lose the memory, lose the engagement. Then we maybe lose the care. Then we maybe become totally indifferent. So not to get too down into that rabbit hole, but it's incredibly crucial that we learn how to use these, learn how to use them well. And there's one thing important that I want to note when using these. These are built on existing information that has been scraped from the internet. So there's a lot of ethical dilemmas and conversations happening right now around this particular topic. What I highly recommend is being transparent with your use of these models. It is not a crutch, it's a powerful tool, but call it as such. Refer to the code written by these AI LLM models as such. Don't try and claim it as your own. Be specific about which code is written by these LLM models. Now we can jump into this last section, which is an introduction notebook to AI-assisted programming. To start, as with the other two notebooks, we're going to connect. Now what I've structured here is a series of challenge exercises for both Google's Gemini and ChatGPT. So what we'll see here is how they kind of think differently. And again, it's not what this video is about. I'm not going to get too into the weeds about how they actually operate and some of the differences between their tunings. But what I am going to show is a couple of differences and show, maybe some successes and failures and how we can take advantage or use them to our advantage. Okay, so to go ahead and get started, these models are text generation models that respond to given prompts. So the way that these interfaces now with these LLM models are built up is basically taking in some text input and then giving a text output. If you've used ChatGPT, then you may be familiar with this already. So when we're trying to get them to write code, we want to specify a few things, like the type of inputs, the type of outputs that we may have or want, and also maybe the programming language, or maybe give specific references to specific functions that we want them to try to write. So again, I'll just mention that both of these are powerful tools in helping us to debug or explain errors, but they're also incredibly powerful generative tools. So in this notebook, I have a couple of prompts to Gemini, and I use the same one for ChatGPT to see the differences in the output. So the first one here is write an image processing script that creates recursively subdivided cells and shuffles them, overlaying them onto the original image. So I've been intentionally vague for certain parts, but then I've been intentionally very specific about things like recursively subdivided cells. So some things I'm really being clear about, and others I'm allowing, us to see, I guess, what these LLM models really have to offer us. So I already have this code baked out from what I generated. We can take a look at it. It's not important that we know how to kind of rewrite this. In fact, that's part of this excitement about cognitive offloading, is that we no longer necessarily need to know this. It is important, however, to be able to evaluate the output, and then also to know enough about programming to evaluate the code itself. Why is this especially important? What if the output's not quite right and we want to tune the parameters slightly? If we don't know anything about the code, we're not going to be able to control the parameters. And what's the best thing about computational design is that we have control to build our own tools as then the authors and designers with those tools, meaning we have full control over the parameters because someone else hasn't built our tools for us. We build them ourselves. That's incredibly exciting, and that's when we have enriched design experiences and processes. Now, it doesn't mean you have to write all of your own, but knowing how and where you can influence those input parameters is crucial, whether you're just an expert user of a software or the developer of it. We have code here, and I'm going to just call out a few things. So one thing is, we take an input. Well, this input, I've actually augmented slightly to use the kind of nice cleaned up interface inside of this Jupyter notebook. But we're feeding in an input image path, and then we're also saving out an image, not using OpenCV. So for whatever reason, these models default to using Pillow, which is another image processing library. So they're importing and installing Pillow. It's what they default to. I'm fine with that. I default to OpenCV. So saving using the save function there and titling that shuffled image. If we double click to hide that code again, we have our file name input. If I open our folder, we can just upload an image, input that file name to reference that as our input image. So this will save as the variable file name, which is our input image. It will process that code based on the code generated from our prompt. Write an image processing script that creates recursively subdivided cells, blah, blah, blah. And then we'll get an output image saved under that file path that we saw under that save function. We're fed into that save function. So what's first? Let's upload an image. This image is uploaded. Let's copy the path. Now let's click play, and let's see what Gemini's given us. So it has done what we've asked, a particular version. It's broken it up into square blocks, square cells. It's randomly shuffled these cells, and then it's recomposed the image. It's not really doing the recursive subdivision now, is it? It's dividing it, but it's not doing it recursively. Let's take a look at what it's actually doing. So it's subdividing, and it's looping through. Let's see if we can get more variation here. Let's see how ChatGPT did. So let's paste that file path here as well, and then refresh, and let's take a look at that GPT output. Pretty similar. So we're getting a pretty similar output from both the Gemini output as well as the GPT output. The GPT output did run a lot faster. Now that's because this code, you can already tell, looks incredibly efficient compared to our other one. So we have really tight, kind of bundled, efficient programming from ChatGPT, and the Gemini code looks a little bit sloppier, although it is the same basic structure. So we're getting the same basic structure. This one did run quite a bit faster though. So for both of these, there's pretty much just one level of subdivision, which we're getting evenly sized squares. So what if we want to be a little bit more specific? What I'm going to do here is I'm going to give an additional prompt, and we can put this in a text cell above here. Actually, I'll move this down one, and I'll say, let's say prompt to Gemini 2. Highlight all of this and make it italic. And now we can determine how we want to change this prompt to get more of that recursive subdivision. One way that we could do this is we could use a quad tree algorithm to divide the image up. So this is a type of JPEG compression algorithm. It's also useful in many other ways, but in particular it's useful for JPEG compression. We wouldn't know how to prompt this if we didn't know the base programming. So I know what a quad tree is, so I'm able to tell this to write me a quad tree algorithm. If I didn't know it, I wouldn't be able to say it. So a lot of people are trying to use too much cognitive offloading and they forget to learn the basic structure. Why is that crucial? We can't prompt it for what we don't know. So how might we change this language? Write a Python script using a recursive function call for 8 generations that reads in an input image and differentially divides the image using a quad tree subdivision algorithm, outputting a resultant image. We've now got a Python script. There you go. We've now got a much more descriptive prompt. So now how do we generate code with this prompt? Well, we can make a new code cell. We can click generate, and inside of our Jupyter notebook, we can just paste that prompt, hit enter, and Gemini inside of the notebook will actually fill our code cell with that particular code. Then we just need to check it out and see what the inputs and outputs are to kind of understand the structure a little bit. So it does look pretty similar to what it was doing in the first place. It is keeping for us our nice clean notebook user interface options, which is great. So that's going to be our input. And actually it keeps the same value for the image as well. So if I click play, we now should get an output. This one here. So the one above, we should get an output. We can refresh, quad tree subdivided image. Looks like it's not quite doing the subdivision. So let's take a look at why that's not working. So it looks like we have a threshold value here that we'll probably have to edit in order for this to work. Let's try a lower value first, hit play, and then let's check the image. We still see no divisions. So if we continue to have problems here, one thing that we can do is select all of our code, and then we can already go into ChatGPT. So instead of just starting with generating the code, giving it its unique prompt, we could do that and compare as well. But we can also bring this from what Gemini created, which seems to be the right structure. But what's happening is our colors here are not giving us the right value. So right now, if I just delete this is what we have. Our color values are not giving us the right values, so it's not checking the variation for the quad tree properly. If we want to get that variation right, we have to fix this region cropping here. So there's something going on with that region cropping. So we can just go ahead and go to ChatGPT. We can open up ChatGPT in the browser. We can say, fix this script, so get colors does not return none. And then we can say colon and paste our script. And if we scroll down, we can see that ChatGPT not only gives us code that works and runs, hopefully we can test that, but also identifies the particular problems in that code and describes the changes that it made. So you can adjust the max color parameters and threshold according to your needs and image complexity. So if we now copy this, so copy that code and paste that, and then ChatGPT doesn't save our Jupyter Notebook interface inputs, so we can just take those from one of these other ones, which is just to declare @param and then type string. So we just need to grab that and set that next to our input there. So next to this input file name, we can say @param type string. Okay, now we can go ahead and see if this code, by increasing the max colors, if this works. So let's go ahead and hit play, refresh, and take a look. So it's not looking like it works there. So I actually have a similar version, and again, this is a kind of augmentation of working with these AI models with my existing knowledge. So I'm gonna give another suggestion to ChatGPT, and I'm gonna say, get colors is still returning none. And we can even use punctuation there. So we'll just say, then fix the code using a variance check with NumPy, with the NumPy library, I guess. Convert the image region to a NumPy array, compute the variance of the colors in the region, use the variance to determine whether to subdivide further. Exactly, so this is what we want to see. So it's actually a good example of both Gemini and ChatGPT getting it wrong and us having to know a little bit about the structure in the first place to know what to look for. So with that variance check, this is looking a lot nicer. So we can copy that code, bring it back into our notebook, and we can paste this here. And then again, we can adjust our file path by saying @param, and then open curly bracket, close curly bracket, and we can say type string and after a comment symbol. And that should give us our input path, and we have that calculate color variance. Now we're using a particular threshold, which is 500 right now. Let's see if this works. So that should be stored in here, which it is. So this code cell we can run, and we're even printing out those homogeneous regions. And now if we refresh and click on that subdivided image, we see that we get those subdivisions. So now what if we want to, instead of just drawing the lines on that image, we want to say swap each of the cells with one of the other cells in each generation. Randomly swap each cell with another cell in each generation. Well, we can now just go back to ChatGPT and we can say, update this code, and it has a memory, so it remembers which code without print statements because we don't want it to print. So update this code without print statements, swapping each subdivision cell with a random other cell for each generation. Do not draw lines onto the image, but output the swap cell information. So it's saying first track subdivided regions, swap those cells. So swap each subdivided cell with a randomly chosen other cell for the same generation. Output after swapping cells. Create and save a new image reflecting the swapped regions. Great, this sounds amazing for pseudocode. And now let's take a look at what it's doing. So it's still calculating the variance there. It's still structuring the quad tree subdivision. And now we have a swap region. Where is it calling the swap region? So it looks like it's just calling that swap region after it's running all of the quad tree subdivisions, which is, it's fine. That's a particular way of doing it. And then it's saving out as quad tree swapped. Let's override this code. So let's open this back up and override all of this and see if it got a little bit closer. And again, if we want to keep that nice kind of interface option, you just say comment ram, open and close curly brackets, type string. Then we can clear selected outputs there, and we have our input file path. Now we can click play and then refresh, and we get a new output quad tree swapped image, which we get a randomly swapped quad tree image from our original image input. What if we wanted to say swap it, but swap it with the closest image patch to it? Let's go back to ChatGPT and say update the script to swap with the closest match to each region based on SSIM. You need to install a new library here, and when it says bash at the top from ChatGPT, when we use it inside of our code in the notebook, we need to start with an exclamation to declare that as bash and not Python. So if we go back to ChatGPT, we can select all of this code. We should see somewhere in the swap region or find closest region that we're actually using the SSIM function there. And now if we paste this and then run, it might take a little bit longer to run. So it is saying input images must have the same dimension. So we can actually come back and take that error. So input images must have the same dimension. So what must be happening is that since all of the different quad tree tiles are different size, if we were writing this, we might have known that, but ChatGPT is not thinking about that. So we can say, I received this error message, resize each tile before swapping. So now each tile will be resized, and that same code is written out, or at least the updated version of it. So we can now copy all of this, and we can override everything except for our pip install. We'll just leave that pip install, which actually installs the libraries for scikit image, which gives us some access to things like structural similarity indexing. Now if we click play, wait a moment, and then we should be able to refresh. So we are getting another error. And again, it's saying input images must have the same dimensions. So let's see where that resize was actually placed, because I have a feeling it was placed in the swap regions, and it was swap regions, but not where the NumPy arrays are actually being compared in the SSIM. So update the script and ensure that the NumPy arrays being used with SSIM have the same dimension. So we still have to know this kind of structure as we're working to know how to kind of fix the issue and be able to interpret some of these errors or issues. So let's copy this and test it. Let's hit play, and let's see if we get another error. So it's now giving us an error that says not enough values to unpack expected for got 1. and that is because maybe we don't have a closest region, but if closest region is none, so here we can try even debugging with Gemini. So we can use Gemini by clicking explain error and see if Gemini can help us out. So it's saying that the issue likely stems from the list comprehension, where we're actually selecting indexes from that closest region. The suggested changes are listed below. So inside of that swap regions function, it's giving us an update with a different list comprehension method. So we can now override that function and run it again. So it's now finished processing here, and if we double click on the image after it refreshes, we can see the output of that quad tree subdivision swapped resulting image. So it looks like for the most part we have a pretty similarly structured image, but we're swapping some of the darker pixels with black pixels. It doesn't look like it's totally doing what we want, but it is getting us most of the way there. It did take a while to run, so that's 37 minutes to run this swap. Now we could have a lower threshold value, which would maybe result in smaller quad tree subdivisions. So we could just set that by lowering this threshold value. So if we maybe lowered it to 100, it would run quicker, and we would also have larger tiles in the resulting image. If we want to save this, we just right click, select save image as, and we can save it to our local hard drive. So the rest of this notebook is just a second round where we're prompting with a different input. So still subdivided cells, but I'm using qualitative descriptions here, like overlaying them onto the original image, creating densely packed collage with fractal-like qualities. And you can see two different approaches here. So for whatever reason, we've gotten these kind of stripes drawn out by the ChatGPT result, whereas the Gemini result has a little bit more kind of random overlapping present, as though it is a kind of collaged output. So we're getting this kind of overlay of the tiles, but only in strips here, and then for the Gemini one, we're getting a much more irregular pattern. And this is with an old image, so this is the example that you'd likely see, but if we go ahead and plug in our new image reference and then run this, we can double check the output of both of these. So I'm going to plug in that new image for both, refresh our page, and we have GPT output 2 and then collage image. So GPT output 2 still looks pretty structured. We're getting some mixing of the actual tiles, but still same size. There's not much variation. It looks pretty random. Whereas the collage image, we actually do have a kind of floating tile overlapped in space. So there's at least more randomization happening within that. And you can kind of see what's going on in this one as well. Now, the last few exercises that I have listed here are prompts for specific types of algorithms. So we have produce an algorithmic image that is visually complex but has geometric order using recursion. So I'm being quite specific about the kind of type of image that we want to make, but not specifying the exact code. So Gemini has produced this kind of striated diagonal line. And then in the example below, I've asked Gemini to add complexity and color using Perlin noise function. So to that existing script, add complexity and color using Perlin noise function. So it gives us this as a result of that prompt. So, and you can see how it's actually doing that. So we have a recursive drawing pattern being drawn out. We're using a random color value. It doesn't look like we're actually using any Perlin noise. We're just using random. So we're using random color inputs rather than Perlin noise. If we scroll down, we now have an example of a prompt to ChatGPT to produce an algorithmic image that is visually complex but has geometric order. So the same prompt we saw as the first one, and it actually gives us a fractal pattern. So we get a Sierpinski triangle pattern, a recursive subdivision pattern, called Sierpinski's triangle. So this is a little bit closer to what we've specified in our prompt. So ChatGPT, I think, did a better job for this first example. And then here we've prompted add complexity and color using Perlin noise function. So ChatGPT has actually added Perlin noise, but basically just used the Sierpinski triangle as a mask for the Perlin noise. It hasn't added any color. Now we could continue iterating through the prompting until we get something close to what we want, but you can see that there's a quite large range of variation in some of these outputs, and if we don't really know what we're looking for, or we don't know how to steer either one of these LLMs, then it's going to be quite difficult to get something that we're wanting. So the more direct route probably is still going to be programming it yourself, or building out a base structure yourself and using these models to augment some of your skills by troubleshooting for you, debugging for you, working through errors with you, rather than just generating code from scratch and relying on that to be perfect from the start. Now, at the bottom of this notebook, I have a couple of coding challenges. So each one of these, I've left space for you to infill the results from Gemini and ChatGPT, and I have 3 different prompts. So the first 2 prompts, I say, write a Python script that generates an image using Perlin noise flow fields. So I'm specifying a very particular algorithm. So I want to test whether or not both of these models can do exactly that algorithm and what the visualization is there. And then the second prompt is write a Python script that generates an image using whirly noise, so a different type of noise function, and generate an image using that. So we can see, again, in these 2 examples, how they kind of handle that. And then in the third one, what I've done is I've copy and pasted a script from p5.js developed by Steve's Makerspace that draws a random pattern on the canvas in P5. So this pattern is called the 10 print colored squares 2, and it's reference code from Steve's Makerspace. So what I've done is I've pasted it and said, convert this into Python code. So we can see how it does converting between programming languages. Now, again, I cannot stress enough that the citation is incredibly important here, and that you always carry the reference of the source code. So you want to always make sure you're carrying the reference, and also it depends on what you're doing with the code. So be careful in terms of licensing and citation. Please always try to keep the citation and be transparent about how the code was developed. However, this is a really crucial step in the kind of history of both AIs, LLMs even, and programming, is that we can now almost immediately convert code between one programming language and another. So if something was written in C# or Java, in this case P5, we can convert it to Python and vice versa, and it's able to quickly make it accessible in another program where maybe that C# language is not as useful or not typically used, or you're just not as familiar with it. So this is a critical step I wanted to show. However, just keep in mind the licensing and citation is incredibly important here. Once we're done working through these coding challenges and infilling the results and testing to make sure that they work, we can save out any images that we've stored on our server, and then we can go ahead and disconnect. That's all for the introduction to the Colab notebooks.